Hello. As a follow-up to Q-Learning, we are going to discuss today about special topics with regard to sub-goals. And here we talk about the concept of, if you want, artificial curiosity. So we are trying to understand what is the purpose, the biological purpose of curiosity, and how can we implement something like curiosity, explorative behaviors in robots or agents or intelligent systems in a general sense. Okay, let's have a look. Basing on our previous course, we talked today about curiosity. The idea is here that we want to understand curiosity and play behavior as a sub-goal setting in, okay, you might call this sub-goal setting in the context of reinforcement learning. Let's say we just, in the last course we heard about Q-learners, and there we say, okay, it's too difficult for the agent to achieve the final goal as a one-time learning behavior. Instead, we want to do some explorative search inside our environment. And there it arises the question, what kind of concepts would be appropriate to do this explorative to do the exploration, to start the explorative behavior, how to control that in an appropriate manner. And let's be biological inspired and say, okay, we have curiosity in play behavior in animals, in young animals, and we have also our children show play behavior, and also of course we have this fundamental behavior of curiosity. And let's bring this into the context of our reinforcement learning and say, okay, how could this be a model for a robotics behavior that is explorative in some way? That's the idea of today's or this course here, this lesson. Yeah, I don't need to say too much about play behavior in children and teenagers and grown-ups. Play with toys, play with Lego, play board games, play with our computers, things like that. Yeah, so why we do that, why does it make sense, why we have this urge to play, to go into an unreal setting where we try to mimic rules of the real world in some sense, yeah? But some reduced rules, so some abstract reduced rules, or even rules that are completely different. And what is the benefit to do so for us? Yeah, of course, also animals plays, cats play with mice, and or here even more dangerous, they might play even with snakes. And of course, in particular, also cats show this curiosity behavior. Also humans, of course, are curious. Many animals are curious and try to show some, try to explore their environment, and yeah. So one concept is the concept of Homo ludens from Johann Huizinga, and he says, summing up the formal characteristics of play, we might call it a free activity standing quite consciously outside ordinary life as being not serious, but at the same time absorbing the player intensely and utterly It is an activity connected with no material interest and no profit can be gained by it. It proceeds within its own proper boundaries of time and space according to fixed rules and in an orderly manner. It promotes the formation of social groupings that tend to surround themselves with secrecy and to stress the difference from the common world by disguise or other means. This kind of social theory of game behavior or playing humans. Homo ludens means, of course, playing human. And let's speculate a little bit about what could be the purpose of play behavior and curiosity. And our hypothesis right now is to improve the ability to react to tasks and problems in later life or with regard to some particular real world problem. So no unusual situations through play situations. And curiosity improves the knowledge about the environment as a general concept. And we might even more generalize that. We can say curiosity improves the prediction ability about the next situation. And there we see already curiosity. What kind of situations make us curious? To what situations we would react in a curious behavior? What is in contrast to that? For example, boredom. Yeah, what is the point of being bored of something and so just go out of one situation? Of course, we are bored in situations where we completely can predict any result of our actions. Yeah, that would maybe result in us being bored. So if we actually do that kind of behavior, we wouldn't improve our prediction of this environment situation in any way. Go back to machine learning or learning of inside our robots. This gives rise, of course, to the question, how can we implement such a behavior in a useful way? In other words, what is the meaning of game behavior in terms of machine learning, and what is the meaning of curiosity in that context too? Reinforcement learning uses sub-goals. As I mentioned already before, we have these sub-goals, and there, one possible definition of a sub-goal would be defining something like a curiosity, and we want to go into this direction. And there we have, of course, to understand that our brain, in some sense, is very heavily a prediction machine. There are many examples of experiments. For example, functional magnetic resonance imaging. I will just in a second show one. And usually what is the result of these experiments is that the person who is in the fMRI machine, in the magnetic resonance imaging system, he is exposed to some kind of a stimulation, and as a result of this stimulation, the brain produces a representation of that particular stimulus, and that differs dependent on what is the nature of the stimulus. So if it's an auditory stimulus, a visual stimulus, and then of course also what is the particular object that is coming together with the stimulus. This is the person who has the voice, or this is the picture of something, and each of these things, they will produce a different representative representation inside the brain. But if you look closer, it turns out that the representation is not actually representing what is coming through the visual pathway. So there's a visual pathway over many steps. We have the eyes, the retina, etc. and then finally we arrive in the cortical areas, the higher brain areas. And this representation is not what would you say is the current thing that the brain is actually seeing, but rather it is more something like what is the brain predicting to be the immediate future of what is happening. For example, we can look into things like visual flow. So basically a person is moving forward, this produces a very particular motion pattern of things passing by in this motion. So it's basically like a cone of motion that's moving past us with a certain velocity pattern. Very careful experiments will result in a representation where the brain overcomes the delay of information processing that happens from the retina to the visual areas in that way that it not represents some object at a real position, but it rather represents the object where it would predict it to be, overcoming the sensory processing delay as a result of this visual flow. Yeah, it calculates already in the own motion, and in this way shifts the representation to the position that is according to the prediction. Also, it's a very common result of these experiments or other experiments where people are represented with some kind of, people or animals are represented with some kind of a reward. And it's a big difference from the brain reaction or also from the representation inside the brain from point of that, if the reward is already predicted, already calculated in, then the reaction will be kind of a almost balanced out, annihilated reaction. Or if the reward is unpredicted, yeah. So if the monkey get a sweet juice and he or she didn't expect that to happen, yeah. So kind of an unpredicted thing. Then of course the brain reaction is much stronger and the monkey will feel much more happy. So also we as humans, we will maybe react not so strong on a birthday cake if we expect that to happen. Of course, every birthday maybe many of us get a cake, so it's maybe not so strong a reaction, but we will react much stronger on surprising positive events. So there our reward will be, the internal brain reward will be much stronger. And yeah, so it makes much sense to look as the brain think of the brain as a predictive machine in a very general sense. I will show one example for that. Or psychophysical experiment from Hüttel et al. In 2002. This was a Nature paper then, and it illustrates how much the brain tries to extract patterns in temporal sequences and tries them to use to do prediction. So this is a very simple example. What has been done in this experiment is that a random sequence of round and square fields have been shown, and the interval time is 2000 milliseconds or 2 seconds, and the brain tries to extract regular patterns out of that. So in this random sequence it always happens that there's an alternating pattern, for example, so maybe round, square, and then the prediction of the brain is that the next one is round again, or patterns of identical things. So we have maybe 4 round patterns in a row, and then the brain would also predict the next one is a round shape. And then they investigate the brain reaction on when these sequences, this predicted alternating sequences or the sequence of identical shapes, these were broken. And in this case, we get a very strong reaction in different brain areas. I just want to show you this example to illustrate how much the brain is a predictive machine, how strong the reaction is on if this, in the case, the prediction is not fulfilled. We have always a strong reaction. We've always also a strong reaction on reward if we have a kind of a positive surprise, and so on. So this is a very important feature in our brain, and there have been whole issues, special issues on scientific papers where they basically illustrate how much the whole cortex is a predictive machine and so on. Physiologically, in the brain, where's this prediction happening and where's this playing a role? And there we have this constellation, basically the pathway of sensory input to the cortex. And interestingly, and it will be an important topic in the next section even more, is that almost all sensory input passes to some midbrain area that's called the thalamus. So the thalamus has different regions that are reserved for visual input, auditory input, and so on. And basically this is then transported further into the cortex. So the cortex is outside the walnut-shaped part of the brain. So this basically, like rays, go out to these different cortex parts. On the other hand, there are very strong connection also back from the cortex to the thalamus, and we will later see that there are some ideas that also this could relate to prediction. And question is, how could this be a useful application for robots, or even here is written for humanoid robots, but how could we use this for this concept, also implement that into robot agents in machine learning, etc. And of course, on the engineering side, they have been predictive concept where we predict in different frameworks or paradigms of machine learning, where we have a predictor and basically also a critic system that interacts with the predictor, basically evaluating how well the predictor works in this moment for various frameworks and various purposes. Here I have just one random example from some older publication where we have here a predictor evaluator. I don't want to go into this publication in particular, just outline one image from the one picture to illustrate. There are of course many other examples. Okay, so we have this prediction concept, and let's say we want to train the predictor, and then how could we put this in a context with curiosity, or in contrast to curiosity, to boredom? Could we build up some mathematical framework that reflects what human experience as curiosity and boredom? And there, of course, also in context of this sub-goal idea, that basically we need to have some concept that helps us to improve our prediction system. Basically, we choose then actions where the purpose is not to achieve some first grade goal, but where we just to explore the space of possibilities of our daily life. And we choose, of course, these actions that would improve our ability to predict the environment better. That would be the idea. So we choose a policy in order to improve the agent's prediction as much as possible. If the agent does not know anything about the environment prior to the exploration, usually it is also very difficult to improve the predicting during explorations. There's a little typo there. The agent is too stupid. If the agent has already perfect knowledge about the environment, it does not have any benefit from further exploration. At this point, I always bring up the example of the little baby, little child. They can spend much time in throwing down objects from the table, just pushing objects from the table and see what happens then. Of course, this is not what grown-ups would do, because they can already predict what is the result of that and don't see any interesting things to happen. In fact, it's just more work to pick the things up again. So they wouldn't do it. Just it's a boring kind of waste of time or something. But for the little child, this has some effect on their ability to predict the outcome of certain actions. The whole paradigm, if you want, we know the action perception loop. The robot interacts with the environment. So we have some action that is caused by the actuators changing the robot's position in the environment or some other features of the environment. And as a feedback, the robot is sensing the environment. Yeah, this is called the action perception loop, and we can of course extend that model, as we did already to some extent, where we have we have some imagination. We did already some mathematical framework. If you like, you could also even call the Kalman filter some kind of imagined environment, where basically the framework of possibilities is boiled down to some stochastic model, which is of course a very good concept. One concept without learning, because we a priori we fill in our knowledge on how the physics of some environment can be updated, but nevertheless you could interpret Kalman filter or particle filters in some sense as some kind of imagined environment. So in some sense as a robot world, the world model in the robot's mind. Yeah. Okay, and of course the next step is not only to let the robot calculate the imagined environment, but also learn. So in other words, to have the world model as a result of a learning process, a training process with regard to the real environment. So the robot learns or is trained by actions with regard to the real environment. We had the Q-learner, this is one example. So we have a reinforcement learning, and of course there basically all these imagined reward values represent something like a set of desired states in contrast to the current state. So we have a current state, and in contrast to that we have in the environment of this current state a set of more desirable states, and the robot would always move to the more desirable states as a result of a learning process. So in other words, it's already some kind of a robot world model. And now the next step is, after we did already this kind of primitive learning, if you want, you would come up with a concept of exploration, where you say, okay, the goal is not directly set by some survival task or finding the door out of this maze or something like that, but we would say, okay, we want to as a sub goal, we want to do first the explorative work. Okay, and this is of course not a completely new idea. For example, Schmidhuber set up a concept of curiosity already in 1991. He says the basic principle can be formulated as follows: learn a mapping from actions or action sequences to the expectation of future performance improvement of the world model. Encourage action sequence where the expectation is high. One way to do this is the following: model the reliability of the predictions of the adaptive predictor as described in section 2. So, of course, this is taken out of journal publication, so we don't see right now this section 2. At the time T, spent reinforcement for the model building control system in proportion to the current change of reliability. So in other words, how securely, how safely we can predict the future of our system with regard to the action reliability of the adaptive predictor. The curiosity goal of the control system is to maximize the expectation of the cumulative sum of future positive or negative changes in prediction reliability. More formally, the control system's curiosity goal at time t0 is to maximize an expectation value of the sum over delta OC of t plus 1. And then here gamma is a value between 0 and 1, closer to 1, is a discount factor for avoiding infinite sums, and delta OC of t is a positive or negative change of assumed reliability caused by the observation of IMT, OMT, and x of t plus 1. For instance, if method 1 or method 3 is employed, then delta OCT or OCT minus OCT minus 1, probably here, where OCT is the response to I am having adjusted at the time. So far the discussion, okay. So basically here is the improvement of the predictability encoded, yeah? So far the discussion did not have to refer to a particular reinforcement learning algorithm. Every sensible reinforcement learning algorithm ought to be useful. For instance, 6 describes how adaptive critics can be used to build a curious model building control system based on the principle described above. The following subsection. Okay, so here's the basic idea. We define here some kind of a cost function where we said, okay, the agent should behave to minimize this or to maximize this cost function with regard to the improvement of the ability to predict a state. So we have a prediction system and we want to improve the predictability. Usually these systems are created in a way that we have a prediction system and a critic that criticizes the prediction system, and then we have a third system that estimates or tries to find an action which would produce, so the critic would give us basically some probability on how accurate is this prediction system, and then we have a third system basically choosing an action of which we can assume that would improve the prediction system right in this moment. That's the fundamental idea. Even more interesting is then what he writes in the discussion. He writes, previous model building control systems are not well suited for uncertain, non-deterministic environments. So he criticizes here what has been published before. In particular, they do not model the reliability of the predictions of the adaptive world models. Therefore, if credit assignment for the controller is based on the assumption of correct world model, unexpected results may be obtained. Previous model building control systems employ some ad hoc method for establishing the world model, for instance, and others use random search to train the world model. Uses a local input-output representation and makes the probability of making a certain training experiment dependent on the time that went by since the system made the last experiment of the same time. These methods work fine for certain problems, but they do not address the challenges of real world tasks in uncertain environments. They are at least two related sources of efficiency which are neglected by these approaches. Not much additional training time should be wasted on exploring those parts of worlds which are already well modeled. To be, not much additional training time should be wasted on exploring those parts of the world where the expectation of future improvements of the world is low. So this is actually a very interesting thought here for the year 1991. This is related to there's already in some sense there's a connection also to brain development. Maybe we can talk about this also at the end of this class. Other parts of this publication of Schmidhuber is he talks about what he calls the confidence model. So nowadays this would be maybe called the critic system. Consider an adaptive discrete time predictor M, not necessarily a neural network, whose input at time t is the real vector and whose output at time t is the real vector O, where the real vector HMT represents the internal state and meaningful internal states are required if the prediction task requires to memorize past events. At a time t, there's a target output DMT. The predictor's goal is to make OMT equal to DMT. Yeah, so basically, we train the network to predict the next state. After having provided a number of training examples, M usually will still make some errors, particularly if the training environment is noisy. How can we model the reliability of M's prediction? Then we introduce an additional confidence model, C, not necessarily a neural network, whose input at time t is the real vector and whose output at a time t is the real vector this, where the real vector h of c is the internal state hc of c. At time t, there's a target input for the confidence model. DCT should provide the information about how reliable M's prediction of OMT can be expected to be. And here you see the related publications they are all from Schmidhuber himself. In what follows, Vj is the ith component of vector phi. E denotes the expectation operator. This was the one from the first of these three slides. Dim x denotes the dimensionality of vector x. C, the absolute value of C denotes the absolute value of scalar C. P of A given B denotes the conditional probability of A given B, and E, A given B denotes the conditional expectation of A given B. For simplicity, we'll concentrate on the case of HC is equal to HMT or equal to 0 for all t. This means that M's and C current output are based only on the current input. That is a variety of simple ways of representing reliability in DC. Okay, so this is the initial idea of Schmidhuber in 1991. And then we come to the Q-learner. He even implements here a Q-learner, a Q-learning system. He will describe how a reinforcement learning method called Q-learning can be used to build a curious model builder. So he implements this into a Q-learner. So enforce the sub-goal, the notation of the same as above. Following 13, we introduce an adaptive function Q for evaluating pairs of inputs x of t and actions a of t, as well as an utility function U for evaluating inputs x. After random initialization of C, M, A, and U and Q, at each time step t, the following algorithm is performed. Randomly select P and then A of t and OA of t, else A of t is chosen randomly. Yeah, so he basically describes here how we can define an action choosing system using a Q-learner, where the Q-learner chooses then these actions that are exploring the environment under the constraints that were outlined before, that we basically have a prediction system and a critic on the prediction system, and then the Q-learner would be trained to find the action where the prediction system can be improved in that way that the critic increases the probability most that the prediction system would act correctly. Okay, maybe we leave it at that for the moment. Maybe it's worthwhile mentioning that there has been also a more clean information theoretic approach on what it's called interactive learning from Susanne Still in 2010, where she gives as a main concept this formula. Of course, this is the formula for mutual information, and she measures here the mutual information between a state action pair and a future sensor input. Yeah, so basically she says here this is the mutual information. This is just a formula for mutual information between the state action pair and the future sensory input. And there she says the quantity I S and S of I of SA, the state action pair, and C is equal to H of C, the entropy, the Shannon information for the future sensory input, minus H of C given the state action pair, measures the reduction of the uncertainty about the future entropy when state and action are known. It is zero if the future is independent of S and A. It is maximal if the knowledge of S and A eliminates all uncertainty about the future. So far, so good. Next time we are going to talk about a special research item that my group conducted several years ago about dreaming. So what are the purposes of dreaming, REM sleep, and how we can implement something like that in robots too. So maybe that's also interesting for you. See you then. Bye.